Well, as we continue to grapple with this idea of electric potential, I've referred to gravity multiple times already, so I want to develop the idea a little bit using the gravitational analogy of gravitational potential, which I did not discuss in our unit on gravity, but I think it'll bring it home a little bit more here with this abstract idea. We'll talk about gravitational potential, which is just energy per mass. Instead of energy per charge as an electric potential, energy per mass. Well, how much energy does a mass have? Well, it has gravitational potential energy, and you divide it by the mass. And simplistically, with the uniform G field, we usually just say mgh over m, which is gh. So gh is the gravitational potential, not potential energy. To get the potential energy, you have to multiply it by mass. Isn't that simple? So here we have two masses in a G field, 1m and 5m. Ug is mgh. And I'm going to use it as an example. The structure known as the Devil's Tower in Wyoming and the associated topographical map, which has all these squiggly lines that are connected, which are lines of constant elevation. And the difference between one line and the next is a certain set amount. Maybe say it's 10 feet or 20 feet or 50, whatever. It doesn't matter. But a given line will be at a constant elevation. And when they're bunched up together real closely, it means the elevation is changing rapidly. So each line is a constant elevation. The G field is essentially constant, so each of the line represents a line of constant gravitational potential. It's at a certain elevation. All right, but then it needs to have a reference point as well. So typically, like it's the Earth's surface. Now, it's independent of the mass, this thing called potential. The mass doesn't even show up there, obviously, because it's mgh over m. So it's just the gh. Now as the mass, or the position, gains height in a G field, the potential rises. Rising potential. So that's one thing that happens. You gain elevation, you gain potential. But I don't even have to say as the mass gains height. You just go to a different height and you automatically are increasing the gravitational potential. Now if the G field is really big, very strong G field, very strong G in the GH, the potential rises faster as H goes up. Now in this illustration here, the 5m, obviously 5 times the mass, has 5 times as much gravitational potential energy as the 1m object. That's easy to understand. But it's at the same, you guessed it, gravitational potential. So it has the same number of the units, which is joules per coulomb. The same amount of joules per kilogram. The same amount of joules per every kilogram of mass is its gravitational potential with respect to the reference point, which would be the surface. So now, understanding electric potential will just be that much easier as we relate it directly to the gravitational situation. Here we have a 5q and a 1q charge in a uniform electric field. And the 5q object has 5 times the electric potential energy as it sits there ready to crash down to this negative plate in both cases. It's at the same electric potential, however, because the E field is uniform, and this distance above this lower plate is the same for both of them as well. So it has the same number of joules per coulomb. Same number of joules per coulomb. So if we have a uniform E field, we do here between charged parallel plates. The work done by the electric field in moving the charge from B to A, moving it across there, is the force times the distance, And that force, as we already know, is QE, so it's QE times D. And that is the gravitational potential energy these charges have if the reference is down here. If it's 0 down here at the negative plate, then this is the electric potential energy they have. So we have UE, electric potential energy, is QED. And that's very closely analogous to our gravitational potential energy of MGH. Now, we know that VBA, potential, is energy per charge, or work per charge in moving it across this potential difference. Well, the work in moving it through an electric field, I should probably say. So I don't have a circular argument. The work to move the charge through an electric field divided by the charge is the potential difference. So work is QVBA, but it's also, as we discussed, as we saw here, it is QED. So QV is QED. The Q's can go away, and we have a relationship now between the potential difference, the voltage, and the electric field, which is just ED. Now this is only true when the electric field is constant. Or we can say that E, the electric field, can be defined in terms of electric potential and distance as V over D, which is volts per meter. So the unit for electric field we see here is volts per meter. But didn't we learn some time ago that the basic fundamental definition of electric field is in fact force per charge? Well, yes, we did. And so we had force per charge is newtons per coulomb. So now we see this perhaps deeper connection between these quantities, namely that 1 newton per coulomb is also a volt per meter. Two ways of defining the electric field. Now, in this discussion so far, there hasn't been any complex mathematics, has there? But I'll bet you're having just a little bit of trouble putting all this together in one mental framework, or a clear intuitive picture about potential, charge, electric field, forces, reference frames, all that. And so that's life. But just remember that there is a couple different ways to define electric field. And it can be in terms of force for a given charge, or the electric field can be defined as the potential difference in a given region of space. And there is a connection there. So that's about enough of potential discussion for right now. Well, if you didn't notice, I was having a hard time finishing off that last slide. So rather than stop the video there, I'll just put one more slide in here with a little example that may take this these abstract ideas that I say are hard to bring all together, and in trying to explain how they're hard to bring together, I perhaps am making it more complex. We'll see it's not really that difficult to apply this. So I'm going to take a look at these charged parallel plates, and we're going to put a potential difference. Don't worry about how we produce that. I'm going to call it a power supply, all right? And it's going to make an electric field across here because it produces a separation of charges. So we have an electric field across 5 centimeters, and there's 50 volts across these plates. All right. So if we have a uniform electric field produced by parallel plates, the electric field is V over D, volts over meters. And so that's 50 volts over 0.05 meters, and that gives us an electric field of 1,000 volts per meter. See, that was easy. And then what if we want to relate that to force? What force would a 500 microcoulomb charge, for instance, experience in this field? Well, Fe is QE, so we have the charge, and we have the electric field. Reverse the order there. So we have micro here, so keep that in mind, 10 to the negative 6, so 0.5 newtons. So that is actually quite easy to apply. A uniform electric field, we got the electric field itself as a relation between the potential difference and the distance. The force is the charge times the electric field, so it comes together pretty nicely. And now I want to discuss briefly the electron volt, which is a unit of energy. It is an energy unit, and it's common in particle physics research because the unit of energy known as the joule is just a little bit too large to discuss the amount of energy associated with atomic particles or atoms themselves. So it's a very common unit in particle colliders. And so here we have the basic fundamental definition that change in potential energy in a given situation corresponds to the charge times the change in potential. Or you could say change in potential is change in potential energy divided by charge, energy per charge. And so spatially almost, this equation, we're going to relate the delta U sub E, that is the energy difference, and it's the electron volt. So I'm going to say the electron volt, and trying to define this unit is the Q, which is, elementary charge, like an electron. Okay, electron volt, the elementary charge, or the electron, times the amount of volts across which that elementary charge or electron is passing. And that's the amount of EVs, the amount of electron volts. Now the elementary charge is 1.6 times 10 to the negative 19 coulombs. So we have charge times volts is the energy. So 1 electron volt, what is it? How much energy is that? Well, it's 1 elementary charge times 1 volt, which is 1.6 times 10 to the negative 19 joules. So that comes out really easy. That unit, the electron volt, this small, tiny fraction of a joule is really useful to define the kind of energies associated with atoms and protons and that type of thing. So we can discuss the physics phenomena occurring at CERN and other particle accelerators with more appropriate units.